introduce some of the key concepts, not only for Lab 5, but most importantly for the statistical part of our course. This is the second module that we will encounter. And here, though it may not seem obvious at first, probability, random numbers, and statistics go hand in hand. So Lab 5 is where we begin to delve into the concepts behind this and, importantly, some of the additional coding that we'll need to use. So listed below are some of the concepts that we'll dig into in Lab 5. So first off, in terms of coding concepts, new area for us will be using the conditional. So here, there's a lot going on. First off, we have a new function called pizza price, and this pizza price function here, so we have to have the def, and we have to have the colon at the end, just as we've discussed previously. And here we come up with a label for the function, pizza underscore price. Again, no spaces, so we often use the underscore to reflect that. And we have one parameter. We're going to call that pizza, okay? This is a placeholder, which will take on a value when we use the function or do what we call the function. So if that parameter, pizza, is equal to, now equals is the conditional. So it compares the value that is stored in pizza, or in this case the string, to this string. So if the value stored in pizza is cheese, then this colon reflects the idea that this price equal to 10 will be executed. In other words, the variable price will store the value 10. Then we come down. So if this is not true, then we skip down to this next statement, elif. So this is what we call else, or else in a way, but here we call it else if, and it's shortened in Python to elif. Elif pizza is equal to artichoke. So here we see prior to this function, we are setting this to artichoke, and this comes into play down here when we actually use the function. So in the use of the function below, we will see that this condition actually holds. So this is a second if. There is another conditional expression known as else, and in the case of else, we do not need a condition because that is everything else. Here, elif is else if. It's like if the first expression does not hold, then we test the second. And if this is true, then we will adjust the price to be equal to 19. Then, as we came down and looked at each of these conditions, then we will return the price, and that will be the value of the function when it is executed. So here, if we put pizza in, it doesn't have to be pizza, it could be anything. But if we put in pizza, which is already equal externally to artichoke. So note, it doesn't matter that I'm calling this pizza. This pizza is the parameter which is internal to the function, or what we call local. This parameter, or this variable, is outside of the function. And then down here, if we put it in, you see we get the value we would expect. That is the price of an artichoke pizza. Down here, we can do the same for cheese pizza, okay? And here we see, this time I just put the string cheese in here. The code went down, and it selected the price of 10. Now note there's double quotes here, single quotes here. It doesn't matter. The single and double quotes are designed to denote a string in either case. So This conditional plays out in the early part of Lab 5. And in that case, you're going to develop this pizza price function, but you're going to have more pizza types than the ones shown here. So this is hopefully helpful as you construct your code. Okay, second type of thing here, this is what we call a loop. Again, we see the colon, but here we don't have if, we have for. This is, going back, this is the for in structure. We saw this in list comprehension, but in this case, if we go through the pizzas, how did we get the pizzas? Okay, here, this np, this is Numpy from up here, that's the abbreviation, random.choice. This new function from the Numpy module allows us to select between, for instance, cheese or artichoke pizzas, and here it will select randomly, that's where the random comes in, between these two. Okay, so executing this, and we'll look at some of the code, it will randomly select one or the other of these two, and we'll see it in action down below. So now, as we select these 10 pizzas, this pizzas becomes an array of names of pizzas. And if you have that array of names of pizzas, P will take on each of them. So let's say the first one was artichoke, P will become artichoke. And then we will get the pizza price. Okay. Down here, we start with this cash. It's equal to 0. Now we will add on the pizza price. And so looping through this, as indicated here, this will go through all of the pizzas that were created. So here we can see it in action. The first pizza randomly selected was artichoke. The price was 19. Second was cheese, 10, cheese, 10, cheese, 10, cheese, 10. Now this may not seem random because here we got 4 cheese in a row, but in fact there's only a 50-50 chance of each. So it's really not that unlikely that you might get 4 cheese in a row. Then we get artichoke, cheese, cheese, artichoke, cheese, and then we can print out the total. So you can use your calculator or just by hand satisfy yourself with the fact that if you add all these numbers up, you will get 127. Okay, moving forward, very important point here is here in our first example, we saw the idea of randomly selecting a pizza. So you can see, think of this as if you knew nothing about the identity of the people going to one of the food trucks out here and ordering pizzas, this might be reflective of a group of students from the student population randomly selecting pizzas. They may have a preference. Not everyone goes for artichoke, and some people like cheese, prefer cheese substantially. So it could be in the student population there are more cheese lovers than artichoke lovers, but we're not completely sure. But we are sampling on a given day at a food truck. You might end up with more cheese orders than any other order. Is that typical or not? Well, we might think that it's typical because a lot of people will order the cheese just because it's simpler and it might be less expensive, and there may be other reasons involved. But we can only make conclusions or statistical conclusions if we sample this appropriately and think about how likely it is that a set of people approaching that food truck would order, for instance, 5 artichokes in a row, even if more students prefer cheese. So data any data set we have is a sample from a population. So for instance, these students ordering pizza, that is a subset of the Temple student population going over to the food truck and ordering pizza, okay? We don't know if the pizzas they ordered is reflective of the distribution of pizza choices among the student population. It's simply a sampling. And the reasons why that might not be the best way to sample, perhaps a survey would be better, or some other means, but nevertheless the data set is a sampling, okay? Even if you collect data, say in Bury Hall or upstairs here in Cirque, this is experimental data, but you are sampling from a physical system. For instance, if you're looking at molecules, you're never capturing all the molecules or all of their behavior, you're only sampling, okay? Typically with molecules, the sampling is quite good, but nevertheless, it is a sample. A survey, like of pizza likes, is a sample from the populations. We want to draw conclusions from the data, and then we want to know what the probability or likelihood that that sample mirrors the population. So these are very important ideas. So let's look at how this plays out with regard to the data from the mini project. So here, if we look or consider the data set that we worked with for the Olympic mini project to be the population of all Norwegian Olympians. Now, in likelihood, we're missing a few, so it may actually be a sample, but let's start out considering it that way. So this is the distribution of ages of those Winter Olympians from Norway. The mean or average is 26.07, and we see we get a good distribution. Now let's think about if we draw only a small set of them, so a sample. Let's say, for instance, we're at one of the events and we ask a small group of the Norwegians what their ages are, and we try to draw a conclusion what the typical age is of a Norwegian athlete or Olympian from that small sample. That's what we're going to try to do. So here we can consider 6 Norwegian athletes. So this is what that bar chart looks like. So we found of those 6, 1 was 20, 2 were 22, 1 was 23, sorry, and 2 of them were 28, okay? So that's what we got. The mean we get is a little different, 24.17, but actually that mean is not totally different from the mean that we got, and we'll make a comparison. But nevertheless, this was a sample, okay? And that sample led us to some conclusions, an estimate of the average age, and a little bit of an estimate of the distribution of ages from the population. So now if we compare these two, you can see clearly here, this is what we've got. Now note, the scale is different here. These are only individual counts, so these are much, much higher because here, for instance, there are over 400 athletes here that are actually indeed 23, not just 1. So in our sample of 6, we have far fewer, but we begin to get a little idea of the distribution, and the mean we got was 24.17 versus 25 point. So it is off, definitely. So anytime we take a survey, now taking a survey of simply 6 individuals is probably not enough to get a good sense of some of the parameters associated with, for instance, the age distribution of Norwegian Winter Olympians, but it does begin to give us an estimate. So the point is, with data, we may have more than 6 observations with regard to anything that we're going to be examining. but it will be a sample, and the sample is sometimes the only thing that we can obtain, and we need to understand how likely it is, for instance, that the mean that we observe of that sample, the mean age, is close to the mean of the population. Because the population is always what we're trying to get at, whether it be in the lab or in a survey. So these are important ideas.